Okay, hi guys. Welcome to my presentation, which basically is gonna take you through a research paper that talks about facial recognition using radial basis function networks. So facial recognition is a really hot topic in various fields across machine learning, computer vision, and so on. And feature extraction is used to form the feature vectors that help us classify the images. But some of the problems that are faced is that we need a real-time identification of the faces. But in real-time identification, there is a lot of variance with respect to scale, angle. So the face images are highly variable, and the lighting, the background, the contrast with respect to the surroundings, the facial hair, makeup, all of these are factors that eventually change the feature vectors which are obtained of the face, hence making the classification problem really difficult. So to get the best coordinate system, what we're going to use is we're going to use two techniques. One is called PCA, which is principal component analysis, where each coordinate is actually an image called an eigenpicture, and the eigenface paradigm, which uses PCA to yield projection directions that maximize the total scatter across all face images, will end up retaining some unwanted variations which are caused by these variable factors. To remove that, we're going to use another technique called FLD, which is Fisher linear discriminant. So then the face feature which is acquired by overcoming the drawbacks of the eigenface paradigm while integrating this criteria will effectively obtain us the face features from a higher dimension space to a significantly lower dimension space, which ends up reducing the number of hidden nodes which are used in the neural network. The number of hidden nodes, since they are reduced, the computational intensity of the problem is significantly reduced to such an extent that they are lesser than the input or output layers which are used in the neural network. And these hidden units of the neural network can also serve as input layers to another neural network to classify the face images. Okay, so tell you a little bit about the neural network itself. This is a multi-layered network which is combined with BP, which is a backpropagation algorithm. In that, let me give you a little insight about the backpropagation algorithm itself. So we have input signals which are fed into the neural network, and at every node, the input signals are basically propagated through the network, and at every node, depending on the activation function, the corresponding output value is generated till it reaches the output layer. At this particular layer, we compare these values with the target or the desired values which are to be generated by the neural network, and the corresponding error signal is then back propagated through the the neural network, and these particular error values are used to adjust or change the synaptic weights of the neural network in order to improve the accuracy of the classification. But of course, this has some disadvantages in that it is computationally intensive because of the slow convergence nature of the algorithm, and we don't have an absolute guarantee that the global minima is going to be achieved. We may be stuck at a local minima, and the algorithm may you know say that this is the final answer. So this is best suited for high dimensionality space inputs with a small sample set. So to talk a little bit about the radial basis function neural network that we're using, you can consider it to be a mapping from a space R to a space S, where according to the Covers theorem, the whole reason we're doing this is because what Covers theorem says is that in when we have a complex pattern classification problem, so which is the problem if it's cast in a higher dimensional space non-linearly, it's more likely to be linearly separable in a higher dimensional space than in a lower dimensional space. So by adding more independent number of dimensions to your problem, the probability of casting your non-linear separable problem into a linearly separable one is more. And as the name suggests, the characteristic function which we're using over here is a radial basis function, in that it depends purely on the Euclidean norm. And usually we have a various types of radial basis functions, but I think the Gaussian function is preferred among all the other radial basis functions due to the fact that it is factorizable. And as over here we can see that this is the form of a Gaussian network, and so the output of a radial basis function is characterized by this equation. So to talk a little bit about now that we know what a radial basis function neural network is, the next step would be to determine the structure of the neural network that we're going to use. And initially we're going to set the number of radial basis function units, which is the hidden node dimensionality, to be equal to that of the output space. So we're basically assuming that each class has only one cluster associated with it, and we're going to select a cluster, and we're going to set the center of that particular cluster to be the mean value of the sample patterns which belong to that particular class. So we're going to find the mean, and the mean is set as the cluster center. And after this, what we're going to basically do is we're going to compute for any particular class that we pick, we're going to compute the Euclidean distance of every point which is present in that cluster, we're going to compute the Euclidean distance from the cluster center to every particular point, and we're going to find the maximum distance out of all these. So for any particular class, what we're going to do is we're going to compute the distance that class K has with, by distance, I mean the cluster center, the distance between the cluster center of class K and the cluster center of the other classes. I'm going to compute the distance of these, and I'm going to find the minimum distance that exists. And we're going to use this distance to basically check for the conditions of overlapping, and that if overlap occurs between class K and any other class. And we're going to check this relationship using three terms: the radius of class K, radius of class L, and the minimum distance that exists between the mean of class K and the mean of class L. So if the summation of radii of class K and L is less than or equal to the minimum distance that exists between the two centers of the clusters, then we know that there's no overlap. If it's lesser than, then we know that there is some margin that exists between the two clusters. But if it's an equal condition, then we know that there's a border case in that the circle K and the circle L, if I may, basically are touching each other but not overlapping. Whereas if the sum of the radii is greater than the minimum distance, then we know that there is some overlap and that some data points are shared between class K and class L. And this overlapping can lead to misclassification of the overlapped points and must be removed. So let us assume that we have detected an overlap that exists, and since this is undesirable, must be removed. So we'll have to split the cluster into two. And basically the splitting criteria can be of two kinds, where it can be either an embodied cluster or a misclassified criterion. And the embodied criterion basically deals with the case where one particular class K is completely enclosed with another class L. So L, being the superclass, will have to be split into two subclasses or subclusters. And if class K is partially sharing some data points with another class, then we'll have to split class K into two clusters in order to reduce the misclassification rate. So if our particular class, when an overlap is detected, satisfies one of the two conditions, then based on these criterion, they will be split into two clusters, for which the respective cluster centroids will have to be recomputed as explained in step 2 of the previous slides. And based on the corresponding sample patterns which are now relabeled into the new clusters, those particular centroids are correspondingly computed. So we're going to keep repeating steps all the way from computing a cluster centroid all the way up till splitting a cluster in case of an overlap, until all the training sample patterns will meet the above two criteria. So now that we learned how to structure the neural network so that the facial recognition application is used, we now will go a little into how to actually train the neural network, and that we're going to look a little into the learning algorithm which is used. So the gradient descent method which we use is usually slow and is likely to be trapped in a local minima, in the sense that if I have this, there's a possibility that when we start from here, and the gradient descent basically detects and keeps iterating until a minima is found. But as we see from the graph, that this is only a local minima and not a global minima. But according to the gradient descent algorithm, this particular local minima is going to be classified as a global minima, and hence there's an error. So to overcome this, what we're going to use is we're going to use a hybrid learning algorithm which combines the gradient descent along with the LLS, which is the linear least square paradigm, to adjust the parameters. So there are going to be two things that I'm going to talk about. I'm going to talk about the weight adjustment, which is done using the LLS, as well as the modification of parameters of the RBF units, which is done using the gradient descent. So now what we're going to do is we're going to try to compute the output generated by the radial basis function for each particular input, and let's assume that R and S are the input and output dimensionalities respectively. So let's say that for each RBF unit, they're going to generate some output yj, which is given by the formula written over here, or in matrix notation as this. Now, since we know that T is basically the target matrix that we have, it basically consists of all the target values that must be generated for the corresponding inputs. Using the target matrix as well as the output matrix, we can compute the error signal which is generated for each input, and we can find basically the squared error energy which is given by this formula over here, and we must make sure that the error which exists in the system is minimized. So this can be solved using the LLS method, in that the optimum weight matrix is given to us by the product of the target matrix as well as the pseudo inverse of R. The hybrid learning algorithm, as stated before, dictates to us that we use a combination of the linear least square method as well as the gradient descent method. And the gradient descent method helps us find the modification of the parameters required in the neural network. So as we can see in the equation over here, we first have the error function which we have to compute, which is given to us by this formula, and partial derivation of this error function yields us this result, which is basically the negative of the error function, the error signal at the output layer. But for the hidden layers, this value is not directly available, which is what the backpropagation algorithm takes care of. Since the error signal is generated only at the output layer, the particular error signal for that particular node is backpropagated through the neural network, and at every particular node the local gradient is again computed and the synaptic weights are adjusted accordingly. So as we can see over here, the change in the parameters that must be brought are again partial derivatives of the error function, and using the chain rule we have split them into these corresponding values. And as you can see, each of these are known values to us. Tk minus yk is basically the error signal which is generated, w is the corresponding weight vector that we have over here, r is the output of the radial basis function, and this is the Gaussian function that we are using over here. So now that we've come to the end of our presentation, I would just like to brush up over all the topics that we visited during the course of this presentation. We first started out with the image that we have of the face, and we decided that the number of variables which are there with respect to lighting, background, or even the features of the face itself are of a very high dimensionality input space, and we decided that we need to first bring these down and map them into a lower dimensional space. And this was achieved using the principal component analysis, which basically extracts only the important face features that are required for our facial recognition system. We then further projected these extracted face features using the linear discriminant function. We maximized the ratio of the between class scatter and the within class scatter. We then moved on to actually choosing the structure of the neural network that we're going to use. We saw what radial basis functions are, we saw what hidden nodes are, and then we moved on to the parameters of the radial basis function, which would be involved in the training phase of the neural network. And we saw that we use a hybrid learning algorithm for actually training the neural network, majorly due to the disadvantage of the gradient descent method in that of its slow convergence. And so we decided that the hybrid method, which would combine the likes of the linear least square method along with the gradient descent method, would finally yield us the formulae that we saw in the previous slides, which would be used for the synaptic weight updations that finally complete the training of the radial basis function used for the facial recognition problem. Thank you for your time.